So, so we're going to start at 7 o'clock sharply, right?
Mm-hmm.
Okay, hello everyone. So welcome to the today's section, the AsiaGraphics webinar section 25. My name is Ye Pan from Shanghai Jiaotong University. Today we are going to introduce the two speakers, talk about there was a two talk. The first speaker is Sun-He Li from Cast University, Korea, who is going to talk about placing and animating virtual avatars in dissimilar environment. Lee is a professor at the Graduate School of the Cultural Technology at CAST. His research focuses on modeling and animation of the digital humans, avatars, and virtual characters for the application in the VR, AR, telepresence, computer games, and computer animation. So let's welcome, and another speaker is from Miao Wang from Beijing University, and he's going to talk about towards immersive the natural interaction in the large-scale virtual environment. Miao Wang is Associate Professor at the K-State Library of the Virtual Technology and System, Beijing University. His research interests include redirect locomotion and immersive in the virtual environment, virtual character construction and animation, and the neural scene representation and aesthetic for the VR. So first, let's welcome our first speaker. So I'm going to stop my screen sharing. Okay, let's welcome our Sun-He Li, please.
Thank you for inviting me to the webinar. I'm really honored to have the opportunity to introduce my work to you. So the title of my talk is Placing and Animating Virtual Avatars in Dissimilar Environments. And this is one of the topics that I'm currently pursuing in my lab. And actually, I have to say that this is one of my most favorite research topic. Um, right. So I think most of you know what telepresence is. Actually, we are currently using one type of telepresence called Zoom. This is a 2D teleconference. And the idea of the immersive telepresence has been introduced in movies several times. And one of the good examples can be seen in this movie called Kingsman. If you see this video, then if user wears the glass, then the user can see the avatars from a remote place, and you can communicate with the remote people through the avatars who are visiting in your own space. So this is the essence of the telepresence. And I think that telepresence has a great value because it overcomes the limitations of the time and limitations of the distance. And this is not only the story of the movie, but the technology is gradually making it a reality. This is the demo video from Microsoft Research introduced in 2016. And you can see that there is a girl in a remote space on the upper left corner. And by taking the video of the girl and reconstructing her shape into the other room, so that you can make a illusion that the user in this room can see the person as if she is visiting his space. So this is called the avatar mediated telepresence. And when I saw this video, I was really shocked. And actually, my research is computer animation, and I was only focusing on the Pixar type of movie character animation stuff. And when I saw this movie, and I was really surprised that this is one future for character animation, and I wanna do research about this. Um, if you look at this video, this is really surprising and it works well. But if you look at this video closely, then you can see how it is really done so well. So basically, the technique or the strategy is basically the copy and paste strategy, meaning that you just copy the shape of the person and then paste it to your local space, but still, that pasted shape of the user can look real. How is it possible? Well, it's because, in fact, the two spaces are the same. You can see that the single sofa and the wooden block are located in exactly same manner in the two spaces. So the girl interacting with the sofa and the wooden block can be realized exactly in the same manner, a single sofa and wooden block in the other space. But this cannot be the case for the all spaces because, when we talk about the telepresence, we should deal with all different type of, spaces. For example, you know, uh, if a user can be placed in this office, but his avatar should be placed in the office with a very different shape of the space and the layout of the furniture. Then how should they deal with, such a difference? This is really important topic, and we have to overcome this difference so that in order to make this immersive telepresence possible. So I'm going to introduce several research projects that I have pursued to overcome this limitation. One is pretty old research, but still is one of my favorite research. This is to retarget human-object interaction to virtual avatar. And that was published in TVCG 2016. Here, this paper deals with the problem of retargeting human-object interaction. Suppose that this is the problem statement. Suppose that a remote user is interacting with a chair, but in the remote space, the avatar is is near the chair, but the chair looks different. So basically, in this case, it is a sofa. Then how should avatar move in order to preserve the movement context of the user, even though the objects are different, but they are in the same type? So let me first start with showing the demo video. So this is basically the retargeting problem. So here, the yellow character is the user, and this yellow character is interacting with a motorcycle. And suppose that your avatar is interacting with the other motorcycle, but apparently the two motorcycles look different. Then how should this avatar move in order to preserve the movement context of the user? So if you think about this problem for a few seconds, then you will soon realize that this problem is nothing more than the correspondence problem. If you can find a corresponding position from one position in the user space to the other position in the after space, then you can solve the problem, right? So, so for example, you suppose that you have two objects, two exactly same objects, then this correspondence problem is easy, right? Because the point here can be uniquely mapped to the corresponding point with respect to the other object, the same object, okay? But the problem here is that, we are given the different objects of the same kind. Right? In this case, we have a motorcycle in the user space, or we have a bicycle in the avatar space. Then given a position here, what would be the corresponding position near the bicycle? This is the problem that we should deal with in order to make the avatar movement possible. So in this work, we have proposed one solution, which is called a spatial map. A spatial map basically defines one-to-one correspondence between the spaces. Here, I'd like to focus on the space rather than object itself, because object correspondence has been studied in computer graphics for decades. So it is kind of some solved problem. But in this case, for the telepresence problem, what we need is not just the correspondence between the surface or the object, but we also need the correspondence between the space enclosing the object. So we call it a spatial map. So suppose that somehow we have defined a spatial map that maps one space, user space, to the avatar space. Then a movement occur or in the user space can be directly mapped to a movement in the avatar space, right? So let's see how we can define the spatial map. Geometrically, we can say the spatial map has three components. One is the external boundary, and the other is internal boundary, and of course in the space, and the third is the space. And we need to define those three components. But let's first look at the internal boundary. Internal boundary is basically the surface of the object. And in order to define the internal boundary, we use some existing techniques. For simplicity, we did not try to deal with all the complex mesh itself. Instead, we created a surface that is closely wrapping the given object. And we developed a genus zero mesh that is closely, tightly wrapped the object. After that, we found the correspondence, the surface level correspondence between the two objects. So that the handle here, it corresponds to the handle of the bicycle, and the point of the wheel is corresponding to a point on the wheel. So this is the internal boundary map. The next is the external boundary. The external boundary defines the extent of the interaction spaces. So it should be big enough so that the space outside the external boundary can be considered not related to the object. In our research, we use the spheres of an identical size as an external boundary for two objects, so that the map between the external boundaries can be simply an identity map. So this guarantees smooth retargeting of a motion that crosses the external boundary. Now we have defined the internal boundary and external boundary. Then we are ready to deal with the interaction space. Well, so interaction space is continuous space, but in order to make computer deal with it, we need to discretize it. So we first discretize the space into tetrahedral mesh sets. And we use a tetra software to decompose the space. Now we have tetrahedral mesh. Okay. So now we have a tetrahedral mesh for the user space. And what's missing in our problem is the tetrahedral space mesh for the avatar space. And here, in order to obtain the tetrahedral mesh for the avatar space, what we did is our strategy was to deform the user space tetrahedral mesh to fit the after space boundaries. So that means we deform the source space such that its internal boundary coincides with the internal boundary of the target space, and its external boundary coincides with that of the target space. Meanwhile, we minimize the distortion of the interaction space so that the movement of the user space can be as close as possible to the avatar motion. So mathematically, it can be written as that one. So we use the Dirichlet energy as a minimizer. So basically, we minimize the Dirichlet energy so that the tetrahedral mesh deforms minimally to fit to the avatar space. One nice thing about this is that the two tetrahedral mesh has the exactly same topology, right? So that means one tetrahedron on the user space have the corresponding tetrahedron on the avatar space, and we have the correspondence between the two, right? So by using that correspondence, we can map a point in a user space to a point in the avatar space. This is simple. So first, given the position of a point, you find its enclosing tetrahedron, right? And then you can identify the corresponding tetrahedron of the avatar space, and you can find or you can define the corresponding point by using the same barycentral coordinates of the point, right? Okay, so by using that simple technique, you can define or you can retarget the motion curve in a user space to a motion curve in a avatar space. So in order to make a avatar animation, we use the motion curve of the end effector, namely the motion of the hand, feet, and head. So given those curves, now we are ready to make a avatar animation. And avatar animation was made by an optimization, by solving the optimization. So we used four energy functions. One is the Auger interaction, and the others are pose preservation, smoothness, and balance. The Auger interaction term was to bring the target end effector, for example, the hand, to the desired position of that hand. Okay? So that's the Auger interaction. And also, we want the after pose is similar to the user's pose. So we define some direction vectors that represents the pose of the user, and we wanted to minimize the difference of those direction vectors. Thirdly, we want the movement of the avatar as smooth as possible. So we reduced the difference of the joint angles of the nearby time frames. Lastly, we used the balance term. We found that without the balance term, sometimes the created avatar movement was not realistic by breaking the physical realism. So we wanted the avatar to move while it's maintaining the balance. So made sure that its central mass comes into the support polygon so that the avatar's motion look balanced. Okay, so that's everything about our technique, and it's time to see the demo. So let's see the case of a chair sitting on a chair. So these are the two chairs, and this is a user's chair, and this is the avatar chair. So given the chairs, we create the watertight meshes and we find the correspondences between the surfaces. Now we discretize the volumetric meshes and find the interaction, find the spatial map. After defining the spatial map, then we can create the retargeted avatar motion just by solving that, the optimization problem. So this is an example of, sitting in front, and also, we can make another style of the sitting, and you can see that overall style and the context of the user's motion is well preserved to the avatar. Since I was interested in telepresence scenario, uh, I also did some experiment for the augmented reality. So here I'm showing you the two chairs. One is the wooden chair and the other is a sofa. And we capture the motion of a user here and then retarget his motion to the avatar on the other space. So you can see that, so this is a resulting motion. You can see that the overall context of the interaction between the user and the furniture is well preserved. Right? So the avatar touches the overall the corresponding position of the furniture. Okay. Right. So that was pretty, interesting effort and interesting result, but it's not, cure all approach. It has some failure cases. We found that this approach doesn't work if the two objects are too different, like a size is too different, or the kind the category of the furniture is different. So it fails to retarget motion for significantly different objects, and also we could not construct a spatial map if the object has an excessively concave shape and the cross-surface correspondence was not continuous. Okay, right. So that was the first success of our research, and we want to, continue to deal with a larger problem. And so we tackled this problem, which is called the placement retargeting of a virtual avatar to dissimilar indoor environment. Since I don't have much time, I will skip the introducing the previous work, and let me just dive into my research problem. So in this particular problem, my target scenario is this. Suppose that we have two spaces, space A and space B. And in space A, X is living and Y is living in space B. And suppose that, the X and Y sent their avatar to the friend's house. Okay? Then the first problem is that if you want to send your avatar to your friend's house, then where should the avatar be located? That is the very first problem that you should tackle. And interestingly, not many research has been, developed to tackle that problem. In this particular case, suppose that, Y is here and his Y's avatar is right here and X is right here, then we want to solve where to put this X's avatar X prime in space B. Mathematically, we can frame this problem as that we want to find the placement of X prime that maximizes the similarity between X and X prime given the X position and Y position and Y avatar's position. Okay. And of course, here the problem he is the problem boils down to defining the similarity between the placements, right? So the challenges of this problem are the first, what are the important features to be preserved for telepresence? And the other one is what feature is more important than the others? Lastly, is there a ground truth for avatar placement between different spaces? Apparently, there's no ground truth, there's no, the ground truth solution. At the end of the day, this problem is the matter of a user's choice, right? So we need to be able to predict what user would want to place their avatar, right? So our approach was to ask the crowd. So here, this is the overview of our approach. So in order to ask the crowd, we performed the user survey. Okay? After that, by looking at the data, we identified some important features to define the similarity of the placement. Then, by using those features, we trained a neural network to predict the similarity between the placements. And after that, we implemented the placement of the avatar. So, right. So this is how perform the user survey. Here, given a person A and avatar Y prime and person Y, we asked the users, we recruited the users and showed this scenario and asked the users to put your avatar in the right place. And we gave the same problem to 10 different people and collected the data. The user collected the data as by dragging the position and root and orientation of the avatar in the virtual space. Here I show you some the results of the acquired data. So given this problem, suppose that this is the X, the user, and this is the avatar of Y, and this is space Y, space B, where Y is located right here. Then many users put their avatar, the X's avatar, around this sofa. And this is pretty reasonable selection, right? Because you are sitting here because you want to talk to your friend, and also the spatial angle are around 90 degrees, and also you are sitting and you are in front of the desk or table, right? And this is exact, the same situation. So many people selected this position, and this is a positive case. And in order to train the network, we also need the negative examples. So we randomly selected the placements that are treated as the negative samples. So for a total of 800 questions from 24 different pairs of house models, we got similar pairs for 10 user responses, and we got dissimilar pairs for 110 random samples. By looking at the data, we identified some features, and we found that those four categories of features are important for the after placement. One is the interpersonal relation, meaning that the distance between the users and also the angles between the users are important, and they should be preserved. Another important feature is what the user is watching or seeing, because we cannot identify the exact furniture or exact object the user is watching. We considered all the objects included in the user's viewing angle or field of view. Okay? The third, we want the avatar to take the similar pose as the users. For example, if a user is standing, we want the avatar to be standing. And if the user is sitting, then we want the avatar to be sitting as well. And that one depends on whether the avatar or the user is seatable place or not. So we represented the furniture as a height field. So that was a third feature. And lastly, we want the avatar to be in the same room as the user. For example, if the user is in the kitchen, then we want the avatar be in the kitchen as well. And the attribute of the room, for example, like a kitchen, living room, is determined by the attribute of or the category of the furniture. So we considered the categories of the furniture nearby. So those are the four the features, and we quantified those features. After quantifying those features, then we trained the network so that it learns the similarity between the placements. So here I'm showing you the positive pairs and negative pairs. So those are the positive pairs, and these are the negative pairs. And we fed those positive pairs and negative pairs so that this metric network can learn such that those two positive pairs are close to each other in the latent space, and those negative pairs are far away in the latent space. Okay, so this is how we learn the similarity. After learning the similarity, the last problem is to find the placement of the avatar. Suppose that this is the user, this is a boy, this is a user. We want the placement of his avatar in this space. Since user has already been placed, we can compute the feature of this placement, right? And given that, and we take some discrete number of samples of the avatar space, and we identify the sample point which has the most similar feature to the user's placement feature. Okay, and starting from that point, we perform the particle form optimization so that we can fine-tune the placement of the avatar. Right. So this is the snapshot of the result. You can see that here in this space, the user X is sitting in a sofa and watching the TV. And here in the space B, the girl is also sitting in a sofa and watching the TV. Then our research places their avatar such that they are watching TV at the same time or together. On the right-hand side, you can see that the user is sitting in a chair and watching TV. But here in space B, the girl is just standing and look and she's standing near the table, right? But in that case, the the girl's avatar is also standing near the table, and the boy's avatar is sitting and watching the TV. So we verified the performance of our technique in the VR, and we also tested our method in AR space. So this is the demo. So here I'm showing you two spaces, room A and room B. And here room B, the user in room B is first moving, and he's moving to sit in a sofa to watch TV. Okay. And after he's placed, his avatar here, shown as a female, a girl, is placed in a corresponding place. Okay. Now, the user in room A is sitting in front of the desk, and after that is completed, his avatar is also placed in a corresponding place. Now, the user in room B is walking towards to the avatar to look at him. Then you can see that his avatar is also placed so that they can see each other and say hello. Right. So this is kind of a placement problem realizing between the two spaces. So I have 10-ish minutes, so I can show you the last work that I have prepared. Right, and that is the real-time retargeting of dating motion. Right. So this was continued effort for our telepresence avatar motion generation. So this is a similar, the same motivation. So the two users are living in a different spaces, and they sent their avatar to their friend's house. And now let's take a look at this situation. So here in the local space, a user is communicating with the friend, and suppose that he's pointing at a certain polygon in a TV, certain position in a TV. Okay? And suppose that the remote space has this configuration of the furniture. If you just copy the user's pose and paste it to the avatar, then probably the avatar will point at some nonsensical position, right? Because of the difference of the space, this scenario uh, uh, underlines the case that the avatar's pose should be retargeted so that he can preserve the motion context of the user, right? So if it's retargeted well, then probably the avatar should not point at this space, but it should point at the corresponding position of the TV, right? So this is important problem because usually, telepresence, one of the important application of the telepresence is the teleconference. And usually in the immersed teleconference, they want to use their gestures and gaze for communication. So to solve this problem, we adopted some data-driven approach. So um, let me first show you the demo video after this research was done. So this is an education scenario. So here, user X teaches user Y about the solar system, and user X, and after Y prime, this is a space A, and this is space B, where user Y is here, and the avatar X prime is located here. And you can see that the furniture arrangements are different, and also the objects are differently arranged. Like, the Earth is here, and, the spatial arrangements of the users and the virtual objects are different in the two spaces, right? Despite those differences, um, I can show you
Hello. Today, I'm going to show
that
you
they
3
are pointing
planets.
the corresponding places.
First, this is Earth. Second, this is Venus. Lastly, this is Jupiter. The Earth is the planet we live on. Can you remember? Please repeat my explanation.
Sure. First, this is Earth. Second, this is Venus. Lastly, this is Jupiter. The Earth is the planet we live on.
Now, I think you can get the idea. Right. So contribution of this work was that it was the first learning-based approach for retargeting the dating motion to virtual avatars in this similar environment. Right. So in order to realize that, as I said, we use some supervised learning approach. So first, we obtained a lot of dating gestures, like pointing gestures. Okay, and we picked the two random a pair of the two random motion, and we time warp the motion such that the actions are synchronous. Okay, and given that, so that means that if I play it again, we want that if user is pointing at this position, and if the corresponding position is right here for the avatar, we want the avatar make this kind of pointing gesture, right? So this is the overview of the network. Basically, the network inputs the avatar motion, the user motion, and it processes it to determine the upper body of the avatar. Let me proceed briefly. So for that, we first need to define the features of the motion. And here, in order to be able to generalize over all other, the size of the users, we adopted the angle-based features. And for the output, our output representation is the end effector transformation. And this is the framework, and we don't have much time, so I'm just going to introduce very briefly. So given the history of the motion, the angle net basically accepts those motion, receives those motion input and makes a latent vector and combine it and give to the motion net. And motion net basically given this latent vectors, it computes it outputs the transformation of the end effector, and we use the inverse kinematics to determine the pose. Okay. Especially we adopted the mixture of expert model that was pretty popular in computer animation research. And we also found that this mixture of expert outputs very stable results for our problem as well. Okay. So our network was pretty robust, and even though we trained over a single character motion, we could show that the decaying motion of various users can be created, and our network was really lightweight. It's only 49 kilobyte, and it was really fast, so that it can be used for real-time telepresence application. So let me show you the demo video of the technique. So here, this is an input motion, and we assume that we already know the target position. And you can see that only by looking at this user motion, the avatar makes a smooth motion to point at the corresponding target. So, okay. Right. Excuse me. Okay, so we can use such taking motion for the teleconference. So I'm going to show you the last video, and we made this video as a commerce application. So user X asks user Y for opinions for purchasing clothes. And these are the virtual copy. And this is a physical cloth, and this is a virtual copy of the cloth. And you can see that, the object size and arrangements are different. Like here, the arrangements are different, and the size of the avatars are different as well.
Can you help me decide whether to buy this outfit?
Of course.
Take a look at this cap. I feel like it has a stylish vibe that I really like. Now, check out this outfit. I love this sky blue hoodie. The shoulder design is really cool. What do you think about it? Do you think it would suit me?
Let me see. I agree that the cap has a stylish flair. I really like the color. Oh, this hoodie has a zipper. It looks so convenient.
You can see that the avatar is pointing at the exact same
I think you should
corresponding
go for
point
it.
that the user is pointing at, right?
Can you help?
Right. So we are continuously working on this project, and the limitation of the current work was that we assumed that the targets and the object correspondence was predefined, but in reality, this is not possible. So we have to somehow need to some algorithm to find the object correspondence. And also here, we only focused on the deictic gesture, but that deictic gesture has to be dealt alongside with other range of gestures as well. Right, so that's all that I have prepared, and thank you for your attention.
Okay, thank you very much for your talk. So, either any questions from the YouTube or any places? Okay, I first have a questions. As we know right now, the different kind of the AI technology was very popular. So I was wondering, what would you see in the future that AI technology will going to help the telepresence?
You mean the AR technology, right?
Artificial intelligence, AI technology.
Oh, AI.
Mm.
Well, yeah, that's a good question. So when I perform research about this telepresence, I often encounter the problem that, you know, um, the research uh, that I produced has some, kind of a limited generalization. And in order to make it, generalize over to wider range of people and, wider range of the users, the AI should be more powerful so that, it can be used for the other whole lot of variable spaces and users and situations. And I think that especially the large language model, of course, we know that the large language models are actively introduced to many applications, including computer animations and an avatar. And I'm also seeing that this large language model can really give a common sense to make that avatar motion so that the after motion can be made more realistic and more generalizable.
Okay. Another question is like I see a lot of your research is focused on the body and the location of the avatars. How do you think about the facial expression of the avatars? Do you think that's important in the telepresence, or it's more important to make the body language right?
Oh, that's a good question. I think that the facial expression is really important. And the only reason that I'm not doing the facial expression research is that there are already many people doing the facial research,
Yeah,
facial
yeah,
anything
yeah.
research. But I'm not saying that body animation is more important than facial animation. I think all are very important ingredients to make telepresence possible. Yeah.
Okay. Thank you very much for your talk. Due to the
Welcome.
time limitation, so let's welcome our second guest, Professor Wang, please.
Yeah. Can you hear me?
Yeah, that's good.
Yeah, so can you see my screen?
Yeah, but no
The
slides yet.
shared
Mm,
sorry. Um
okay, that's good.
okay.
Oh,
Okay.
no, it's gone.
Okay. Can you see it?
No. My side is black at the moment. Okay, that's good. Good now.
Okay. Mhm. Okay, thank you. And also thanks Professor Lee for the excellent talk. And actually, we inspired by Professor Lee's work a lot, and we are currently following Professor Lee's work. The collaboration under the similar environments. So today, my talk is about toward immersive and natural interactions in large-scale virtual environments. And firstly, I will show a demo. So this is actually the Apple Vision Pro. It just released several days ago, and it's the spatial computing technique enables the device to seamlessly integrate the virtual contents into the user's environment. And by using the SOTA sensors and cameras, the Apple Vision Pro can, create the surrounding space and position virtual elements in real time, creating more immersive and interactive experience for the users. So this demo is very cool, and the totally immersive VR scenes and also the augmented scenes can be displayed, and the user can interact with the other people with very high quality. Okay, so um, okay, so in virtual reality, there are three eye characteristics: the immersion.
Excuse me, we can't hear you.
Hi, Professor Pan. Can you hear Professor Wang's talking?
No, I cannot. I just text messaged him.
Okay. Let's wait for him for a while.
Yeah. I think he's restarting. Okay, cool. We can see the screen, but no voice at the moment.
How about now? Can you hear me? Hello? Hello?
Hello, we can hear you, but we cannot see your screen. We cannot see
Okay,
your
so I will
slides.
share. I will share my. Okay, can you see the screen?
Yes, but no slides yet.
Okay. Um,
Okay, good.
Sorry for the network issue. So I go faster. So these are the characteristics of VR, and do you expect immersive and natural interactions in very large scale virtual environments? So this is an example. This is an ideal example. The user is playing the VR game, in the large scale virtual environments, and he's also in a very large, very big, the physical space as an underground. Yeah. This is an ideal scenario that the user can have a very big physical space. And in our daily life, users, we use devices in our office, in the living room, so we don't have so big physical space. This is actually what it looks like in our daily life if we play VR game. So we are in a very relatively small physical environment, and the machine can be very large. And the physical space limits the large scale workers. So if the user walk along his way, there can be some collision between the user and the wall or the obstacle. and this can be very dangerous, and the user may hit himself to hurt himself. So challenges we are facing are twofold. First, the limited physical space hinders the user movement. The second is the similar spaces can push on the user's collaboration, and this issue is addressed very well by Professor Lee. And we have proposed solutions to this problem. Firstly, the perception we have to the security level, and we measure the perceptual gains and the potentials for the research. And at the level, we have to align the virtual and the physical environments they're working technique. And at the level, we have released the open source library and benchmark for the redirected working technique. And fourthly, we have proposed a concept to use the proceeds for the distributed virtual environments. And these papers have been published in VR, ISMA, and TCG. So I will go to the first work. So the problem is how to move in virtual spaces when the physical space is limited. So in this page, you can see on the left-hand side, there is a relatively large physical space, and it's relatively empty. But the user can maybe he wants to experience much larger open scene. So techniques for locomotion, the common ones. First is teleportation. The user can throw a parabola to specify the target position that the user wants to go, and the teleportation technique can be used to position him to that place. And the second one is the working in place technique. The user can walk in place on a treadmill, and the mechanical device can help him to walk through it. And the third technique is called redirected walking that we use to make the user experience the virtual environment. So with redirected walking, the user can walk in a straight line in the virtual space, but we can redirect him to walk along a curved line in the physical space. So here is an example of the redirected walking and also short as RDW. So the left-hand side, the user walk along a curved line, and he is redirected by changing his viewpoint very slightly during walking, but he cannot perceive that, and he walks in the tree, but still along the straight line. And the idea to match the passes between virtual scene and real scene. So in the large virtual space, the walking path is straight, and in this optical space, the walking path is curved. So the key is to compute mapping between the sample points along the lines. And we try to do mapping by manipulating the viewpoints of the user during work. So we use games to manipulate the passes. So we control the user viewpoints to stay away from physical space boundaries. There are typically three types of gains: the rotation gain, the translation gain, and the curvature gain. Each gain should be limited within a range, which is called the imperceptible range. Also, the upper and the lower bound of it is called detection threshold of the gains. So, for example, the detection threshold of the rotation gain should be the 0.67 to 1.4. These gains are measured by the user experiments. be used to manipulate, for example, if they use five and the user walk in the physical space strictly and then the people walk in the space at 1 5 meters. Start estimated by user studies, uh, and and I easily and in this in the user studies, users walk along the along the way to target as you can see on the left side. And the procedure is called the two orders to FC. This, I follow currently there was there taking the two position option where the is long compared to the world. The impact data we feed the data from to the cycle mechanism uh, is the S-shaped function. After feeding the data, the gain value corresponds to 50% considered as the subjective equality PSE, and the gain values correspond to the 25% or 75% considered as the upper and the lower detection that regard after you know, and then Can you hear me?
Yes, yes, we can hear you now.
Yeah, that's good now.
Okay, sorry. So I'm using my mobile phone as the
Okay, that's good.
audio. Okay, so sorry for the delay. So we have to I will firstly go over the work. So we have this is our first work that for the redirected locomotion, and our contributions are the design of the two variable psychometric functions for joint measurements, and we estimate and analyze the horizontal and vertical detection thresholds by conducting a redirected jumping user study, and we demonstrate the effectiveness of our findings through the game applications. So to do so, we have to divide the jumping into the states. So we divided the jumping to the standing, the ready, the ascending, the descending, and the landing, and the standing states. This can be detected using the head-mounted display and also the tracker and the controllers. So we can easily determine the states the user is currently in. So this is an example of the real and the virtual jumping states manipulated by the vertical and the horizontal gains. So but it was challenging to for the participants to simultaneously pay attention to the horizontal and the vertical manipulations during jumping. So we have two design choices. The first design choice is to let the user jump once and again, and let the user to answer the question 1 and 2 in a sequence. For example, after the jumping, we let the user to answer whether this jumping distance in the virtual space is longer or shorter than that in the real world. And after this answer, we ask the second question, whether the jumping height is higher or lower than that in the real world, and we get the second answer. But we found that the user it was very challenging for the user to remember the two-dimensional jumping states during one jump. So we came to another solution that let the user jump once, and then we asked him the question of whether your jumping distance is longer or shorter than that in the real world, and let the user answer. And then we let him jump again. And then we ask the second question, whether the jumping is higher or lower than the real world. So we get the second answer. So the user have to jump in two times much than the original than the design 1. The design 2 let the user jump more. So this is an example of how the user perform the jumping process. So he is in the virtual scene and jump, and then answer the question and go back to the original position to jump again. And here are the results. So remark that in previous work, the researchers have used the one variable psychometric function to fit the jumping data. But now we have two jumping directions, the horizontal and the vertical. So our function is two variable psychometric function, and we use the previous detection thresholds. For example, the upper detection threshold, the UDT, as the 75% of the data, and the lower detection threshold LDT is 25% of the data. And we have, instead of getting the curve, S-shaped curve, we now have the 3D surface of the fitted data. So if we look from the top view of the surface, we can have some initial conclusions. For example, if you look at the figure on the left-hand side, so if the vertical gain increases, the imperceptual range of the horizontal gain also increases. And if you look at the middle figure, if the horizontal gain increases and the imperceptual range of the vertical gain also increase. And if we enclose the curves, we can have a area and we can sample gain values within the area that is safe. The user may not perceive it. So we can reduce the required physical tracking space for the VR experience without the user's perception by slightly increasing the vertical gain. And we developed the two applications as a gaming application. So we tested the theory of what we found of the detection threshold of the game. So first, we let the user to play the box jumper game. So we place some boxes in the virtual environments and let the user to jump over the box. So and we ask the user whether the jumping distance in the virtual environment longer or shorter than that in the real world. And in the other application is it's a Super Mario game that we place some boxes in the mid-air and 0.2 higher than the user's head, and let the user to hit the box. And we ask the user whether the jumping height is higher or lower than that in the real world. So this is the user study procedural of the games. Okay, so here are the results of the user experiments. So we use the three groups of the gains. The lower group, we set the horizontal and the vertical gains of both of 0.8, and the upper group we set the horizontal gain as 1.4 and the vertical gain as 2.0. And the control group we set the horizontal and the vertical gain as 1.0. And we have some values of the physical distances. We found that in the upper group, the user jumped shorter than the control group horizontally, and the upper group jumped lower than the control group vertically. And we also found that the lower group, the jumping distance is longer than the control group, and the height of the jumping horizontally is also larger than the control group. So here are the limitations and conclusions. The limitations that we only tested the standard two-legged takeoff jumps, and the measured detection thresholds may not extend the other kinds of jumping actions. And we only explicitly investigate the horizontal and the vertical detection threshold. As a conclusion, that the imperceptible range of the horizontal gain could be affected by the value of the vertical gain and vice versa. And by slightly increasing the vertical gain, we can reduce the required physical tracking space for VR experience without the user's perception. So in the second work, we investigate the virtual physical environment alignment with directed walking. So the problem is, how can the users reach the virtual object while also reach the corresponding real one in the physical space?
So this is the problem. And there are some previous work of the passive haptics. There are some Professor Frank Slinicki in 2008 have investigated the taxonomy and implementation of redirection with passive haptics. So the method is to divide the user's working process into two parts. The first part is more general, to use general redirection process such as steering to center problem to let the user walk in the center of the room as more as possible. And the second state is to perform the passive haptic redirection. This is conducted by the taxonomy. And following Stanicki's work, Professor Lili Wang have proposed a constrained path redirection for passive haptics. So here is the example and a demo of the work. So following Professor Wang's work, there's another work called the reactive alignment (REA) from Gerald et al., which is the best paper of the VIST 2020. So he proposed the artificial potential field for this problem that use a pull force and a push force and optimize the forces to let the virtual and the physical points align. So our contribution of this problem is to propose the transferable virtual and physical alignments. So if there are more than one point in the physical space and more than one point in the virtual space, we can allow the target positions can change. For example, we can let the yellow point as TP2 to match the green point TV2, and we also let the TP2 to match TV3. So in this way, we can use the physical space as much as possible to reuse the positions that can be matched to the positions in the virtual space. And we have proposed a reinforcement learning-based approach to train the method for the alignment. And we have proposed a novel reward function design, including the dynamic virtual physical target matching and virtual target weighting modules. And we have demonstrated this method using the simulation and user studies. So this is the training pipeline. So we feed in the observations of the user, both in the physical space and the virtual space. We use the orientation and the position as the input, and we use the PPO framework to train the network parameters, and the output are the gains for redirection. And the novel one, the novel part of our reinforcement learning framework is that we have proposed a novel reward that involves the distance term and the orientation term computed from the states of the physical and the virtual space. And we have also evaluated our method with the baseline method and the REA method, the reactive alignment method. That was the best paper in VIST. So the travel is our method. We have evaluated the method using the simulations with squared environments with different numbers of the target positions, and the physical distance error and reset per pass statistics indicates that our method are better than alternative ones. And we also evaluated the methods in the rectangular virtual environments, the physical environments with placing obstacles, and the different. Sorry, my sharing there's some issue in the screen sharing, and I think I'm offline on my computer. I think my screen is not sharing. Okay, now it works. So yes, we evaluated our methods using simulation experiments and also the real user experiments. So as a conclusion, we propose a novel and practical technique for VR scene navigation and interaction, and we achieve better environmental alignment results than the sought-out techniques. So the third work is about the platform of the redirected walking. So we have noticed some problems that there is in the redirected locomotion field, the open source methods were seldom available, and there is no recognized benchmark published for accurate and qualitative evaluation of the methods. And we noticed that there is a toolkit named RDWT, developed and released in 2016, but it lacks of the multi-user walking support, lack of the complex scene support, and the reinforcement learning support and sort algorithm implementations. And there are actually a lot of locomotion techniques with different redirection controllers. For example, the subtle ones and the overt ones. There are the classic algorithms that steering to the center, and also the artificial potential fields, and also the deep learning based methods that need to be developed or deployed by the users. So the user have to re-implement their algorithms by themselves. So to deal with this issue, we have developed and released the platform called OpenRTW. So our contributions is to support the multi-user working in shape and size varied tracking spaces. We support learning-based models and passive haptic feedback deployment. And the implementations and the open source of the SOTA RTW methods with unified APIs. And we do the quantitative evaluations across methods based on the OpenRTW library and benchmark. So here is the overview of our OpenRTW library and benchmark. So on the left-hand side is the library. We support the customizable RTW controllers and the simulation and the real walking, and also data logging, and we support for reinforcement learning. And on the right-hand side, we support the different tracking spaces, multiple user walking, and general and real walking passes, and the classic and the SOTA algorithms. So here is the library architecture. So we have the movement component, the path component, the sort algorithms, and global configurations, visualizations, and the analysis modules. So I maybe jump some slides. We can go faster. So I will jump the details of the architecture. Okay. So yep. So in our library, we have implemented a lot of algorithms by ourselves with the unique API. So we implemented classic controllers, the sorter controllers, and the resetting controllers with both the rule-based and also learning-based methods. And we support the very detailed evaluation of the redirected working using different configurations. For example, different size, areas, and different methods and different working paths. And we also support the high quality images and the videos that can be used in our paper for the community. And we are happy that several papers have used our platform to implement their paper, their method, and publish their paper. So this is the conclusion of the platform. And then I will introduce the last work, that the room scale environment fusion for efficient traveling between separate virtual environments. So the problem is how to allow the users to frequently travel between scenes, and how to address the dissimilarities in user perception across the distributed environments. So to solve this problem, existing methods allow the users to teleport between scenes. For example, the instant teleportation methods allows the user to walk in the circle and teleport the body to the other virtual room. And the virtual portal technique that allows the user to walk through a virtual door that connect the different rooms. But there are some challenges. Firstly, the occlusion hinders the user perception of ongoing events, and abrupt context changes negatively impact the user's visual connection. There are still a lot of area in front of the user that are blocked by the wall. So we propose the scene fusion technique that we seamlessly fuse the two distributed virtual rooms, and we integrate the distributed room into a larger room by blending and connecting the structure of the walls and blending the textures, so the user can walk directly to the other virtual environment. There is no wall in front of the user. So this is our idea. And we propose the novel design rationale of the environmental fusion technique, considering the efficiency, the virtual plausibility, and the versatility, and enable the users to actively travel between the virtual environments with continuous visual change. And our method with experiments indicates that it outperforms existing techniques on the efficiency, the workload, and the preference. So yes, so my the fusion process is illustrated with a video, but I guess it will be maybe not clear due to the network issue. So I will jump it. So we have conducted user studies to evaluate our scene fusion technique with the prop searching and place place a task, the user have to search for the proof from the one room and pick it up, and using one of the three techniques to travel between the virtual environments, and then place the virtual prompt to the targeted position. So this is a trial of the searching and place task. The users have to repeat this task using either of the techniques, the instant teleportation, the virtual portals, and also the scene fusion. And we have conducted the user studies the whole 8 by 8, the 10 by 8, and 16 by 16 meters. And the results in this user study indicate that our method, sorted as SF, have the shortest movement distance and the least completion time of the task, and the lowest task load of the task. And we also conducted another study that lets the users collaborate. Can you see my screen? Yes. Okay. So the second study indicated that our method still have the shortest movement and the least completion time and the lowest task load. So in this work, we facilitate the efficient traveling between the scenes in virtual environments for single user exploration and multiple user collaboration. And we have our method get the lower time cost, the walking distance, and the cognitive load compared to traditional methods. So I think that's all for my talk, and yeah, and I'm very sorry for the network issue. Yeah. So Dr. Pan.
Okay. Thank you very much for your talk. So, is anyone have questions? I actually have two questions. The first one is, how do you think the advancement in AI can contribute to improve the interaction within virtual environment? Hello, can you hear
Thank you.
me?
Yeah, for sure. I think AI and the yes, I can hear you. Can you hear me?
Yes.
Yes.
Yes,
So
I can hear you.
for sure, the AI and the machine learning technique can greatly enhance the interactions within the virtual environments, and by enabling more sophisticated and realistic behaviors of the virtual elements. For example, the AI algorithms can be used. Yeah,
Your
can you hear
voice
me?
was gone. Yeah.
Yeah. Can you hear me? Oh, sorry. I think my mobile phone network is also there is also some issue. So yeah, I will quickly answer your question. So yes, for sure, AI can help to create more intelligent and more responsive virtual characters or agents. For example, using the reinforcement learning and multi-agent system that can adapt it to the user input, provide the realistic dialogue and exhibit like real humans. And the machine learning techniques can also be, employed to personalize the user's experience based on the individual preferences and behaviors, and making the interactions more engaging and immersive. And I also think the AI and the machine learning can also be applied to improve the naturalness of the interactions by enabling the system to interpret the user's gesture, speech, and actions in more meaningful ways, leading to more intuitive and seamless communications within the virtual environments. Okay, thank you for the question.
Cool. Thank you for your answer. And I had another question. What are the potential applications that could benefit from advancement in the immersive interaction within the virtual environment?
Yes, thank you. So in our demos, we mainly stay in the research problems, and we have shown some applications. For example, the gaming. Yes, I think the gaming is one of the section that can be that our technique can be used to improve the immersiveness, and also I think our method can also benefit the training and the simulation applications in industries, for example, as the healthcare, the manufacturing. They can leverage the immersive interactions to create the realistic training environments that mimic the real-world scenarios and improve the mini outcomes. And also in the field of education, the immersive teaching can improve the learning effect that have been demonstrated by researchers in the other fields. And additionally, the architecture and the device repairment with collaborations may also benefit from our techniques, such as the collaboration, such as the natural interaction. Yes, I think there are some potential applications. Thank you.
Okay, cool. Thank you very much for your talk and answer. I think that's all for today's seminar. So yeah.
Thank you. Bye-bye.
Bye-bye. Thank you all.
Okay.
Hi, thank you. Bye-bye.
Thank you very much.
Thank you.